Welcome back to episode 4 in our series introducing Proto AI's Gestalt AI. Today, we're going to be talking about the cold start nature of the AI. And to start off, Nick, why don't you describe what it means to have a cold start AI and what observations we've had with our AI showcasing its performance in this area?
Absolutely. Thanks, Mike. So for most AI or machine learning models of any kind, training is the first step, whether it be unsupervised or supervised or however you're going about it. The model is trained and it learns and then it's deployed, right? You typically don't see an untrained model just stuck in there and go. That's what a cold start means in this context. Several of our e-commerce deployments actually were done that way. We just plugged in the AI with no a priori data whatsoever and said, go. We didn't tell it, what are you allowed to recommend? We didn't tell it what they sell on the website. We didn't tell it what web pages were on there. We literally didn't tell it anything. The only way it figured any of that out was by watching the traffic on the website. And through that, it saw, oh, okay, they just sold this item, this item, and this item, and this item. That means these are sellable items. Okay, I've seen this guy go to this web page, but this web page never results in a sale. And it worked its way up, and eventually it developed its own understanding and built its own internal model for that from scratch. Now, obviously, results varied a little bit, but in general, this resulted in about a 5 to 10x return on investment on a monthly basis. So why does any of that matter? Well, this opens up a big set of opportunities to serve customers that might otherwise not really be able to take advantage of AI, because we don't need a big chunk of training data in advance, as you would in, say, a supervised model where you've got to have a huge input set and a known output set to plug it in advance and build your model up. And we don't need a ton of expensive a priori computation like you do in an unsupervised model, for example, with an unsupervised neural network, like a large language model, where they've got to spend a lot of money just paying for the electricity to run the machine so it can do the computations and then generate the model and use it. In our case, the AI is actually learning in a continuous fashion. And as a result, the model naturally scales with the amount of data made available to it. It's not susceptible to staleness, meaning it doesn't have the, for example, if you were using ChatGPT, it would give a disclaimer. I don't know anything from before some date in 2001. I forget precisely. We don't have that problem because the data is coming in continuously. So it's frequently updating itself and refreshing itself and making sure that all of its perspectives are current. This is also how it unlearns things. If it figures out, hey, wait a minute, I really thought that was true, but I haven't seen any evidence of it in a while, so I'm going to unlearn it. Right? That's how that works. Now, initially, when small data is available, so early on in the process, what actually happens is the model and the AI learns the major factors quite quickly. So in the case of e-commerce, it'll figure out, okay, these are the 10 major products on this website that sell frequently, right? Maybe you turn it on and within a couple of days, it's seeing, all right, this one sold 5 times, this one sold, whatever, depending on the traffic of the website. Those will generate the initial set of knowledge available to the AI. But as more data becomes available, it will explore and learn with greater nuance. So we'll start figuring out, okay, this product doesn't come up that much, but this user's behavior matches the people for whom it did come up. So I'm going to bring that up just in case they might like it. Things like that start to happen as more and more data comes in, as it gets a chance to learn about periodic trends, start to figure out, hey, wait a minute, it's this time of year again. Maybe it's December or whatever, or it's post-Thanksgiving with Black Friday, Cyber Monday. That's the sort of thing it'll pick up with more time, but it has that initial level of functionality very quickly. And it does this entirely unsupervised. It maintains this applicability at scale without any help from me, Jeff, anybody else. It just sees the data that comes in, figures out the relevant information in there, and updates its model as it goes.
With the capability of the AI to learn from a cold start, it was critical that we find methods to let it learn rapidly. Jeff, can you talk about how we went about solving the utilizing the few shot technique?
All right, so when I take a look at how symbolic AI is developed over time, there's an experiment that was run in 2021 by IBM that I took particular note of. What they were trying to do was get an autoregressive neural network to discover images and learn them with very little training data, and then be able to use it at the same reliability as having the normal saturation training that typically occurs. So they were looking for a very rapid training cycle in that. In that particular experiment, they built an analog memory storage and computational system on a bench, and they ran this system to train on 500 examples of different things they wanted to know, and each example had 5 instances of that data, different variations on it. The AI successfully trained in that case with only a 2.7% loss in accuracy in 5 events. So that was a pretty significant trick they pulled off there. They really got down into using analog signal instead of digital expressions. Instead of measuring it by countability, they measured it by the expression of energy. There's a lot of things going on there that they did. But what happened was they were able to get good results with very little training data, very little success data. So when we go to our AI for deployment, well, before I go away from the IBM experiment, I want to go to what their article said specifically. And the article that I'm citing here, so everybody has it, is called Mimicking the Brain, Deep Learning Meets Vector Symbolic AI. It was published in April 29th of 2021. So in the article, IBM researchers cite this: the ultimate goal, though, is to create intelligent machines able to solve a wide range of problems by reusing knowledge and being able to generalize in predictable and systemic ways. Such machine intelligence would be far superior to the current machine learning algorithms, typically aimed at specific narrow domains. So what happens in what they're trying to discover in their test is, if I'm just given something that it doesn't really have a model built for, can I sit there and observe cases of success and form my own understanding, or its own understanding, of what the success of that information is when it's seen with a real world case? So that's a pretty big bar they're trying to get across there. So when you go to our particular Gestalt AI doing this symbolic learning, it's learning with no prior information at all. It's starting from a blank slate. And as it sees the presented information, it discovers which things are successes, which kind of things influence the possibility of a success, what kind of time dimension and time expression there is, and whether or not it's true now. All of those things are being done without any other systems involved, and it's doing it on a kind of a continuous update basis, adding more and more nuance and detail to its understanding. One of the advantages of our particular deployment model is we don't really have a case for creating a delusion. A delusion in artificial intelligence is when an AI believes something that's false and believes it stubbornly. And that kind of effect occurs if you start doing a lot of feedback on that information coming back in to retrain with. So when you start doing these recursive feedback loops, that's a risk that you always face in the training data. Because our technique is completely different than that, we have exactly the same rate of learning something as we do of unlearning it. Typically in neural nets, the amount of data it takes to unlearn something is quite a bit larger than the information it takes to learn it. So undoing its present understanding is a kind of a difficult, ongoing, high data requirement to get it to correct itself out of a problem. In our case, we're very clean and smooth with that process. If a process presents in a way that says the data is not true now, it'll simply attenuate it out and has less chance of it being used. And if it reappears, it'll come back in, and then it begins to see periodicity and all kinds of things related to that as it's looking at this data over time. So when we deployed our zero-shot training event, that happened in November 21st of 2023, and in a very short period of time, the AI identified 50 different classes that it was looking at, and in 156 few-shot events, basically about 3 per exposed data point, it started getting very, very successful. Now, the advantage of that was we were able to create a direct revenue lift of 16% coming from a cold start in just a little bit of time. That's an enormous effect for a company out there that has no AI expertise, doesn't have training data. This is as close to AI plug and play as you could possibly get, where you can just say, okay, we have a problem we can solve, we're plugging it in, and it's adapting to your environment and knowing how to apply the solution to your use. And that direct alignment is fully automated. You don't do anything to make it happen. The goal of getting this kind of symbolic learning in artificial intelligence is you're looking for the possibility of creating mathematical invariants which are transferable. And when you get to that level, it becomes mathematically possible for you to use those effectively what you would find in physics being a Planck's constant or something like that, where you can apply that equational structure to solve something reliably in a whole series of repeated cases. Now you have the possibility of doing that in multiple domains of knowledge and creating the ability to move that information back and forth using that as a high-speed, fast calculation technique. So what would that mean in real application? What we're trying to reach for is this idea that we can plug the AI into a whole host of different environments and still get good effect that's specifically tuned to the environment, but meets the need that's being asked for the solution. And that high fidelity solve in that case, and the ability to learn this and do it symbolically, means we have the ability to extend those solves beyond the boundaries of the domain and also use high quality information techniques in the domain to create chains of cause and effect.
Thanks, Jeff. Our next episode will discuss our case studies and upcoming developments. See you next time.